Solid-state energy storage vault industry development and financial support strategy. Table of contents. Introduction, energy transformation and new demands for energy storage. Industry status and market analysis. Financial support needs analysis. International financial policy cases. Local development proposals. Conclusion and call to action. Solid-state energy storage. Vault, financial policy and development framework. American Sustainable Dynamics Energy Co. Limited presenter, Richard Shih. Date, May 2025. American Sustainable Dynamics Energy Co. Ltd. Email, usa.sustainable.dynamics.energy@gmail.com. Introduction, Solid-state energy transformation and new demands for energy storage. Solid-state energy storage vault. Solid-state energy storage is a battery technology that uses solid electrolytes to replace traditional liquid or gel electrolytes. Due to its high safety, high energy density, long lifespan, and environmental friendliness, it has become an important development direction in the field of energy technology. Below are the core advantages, characteristics, and related descriptions of automated production factories for this industry. What are the types of new energy? New energy refers to energy forms that are relatively clean, renewable, and have minimal environmental impact. Below are some main types of new energy: solar energy, utilizing solar radiation and converting it into electricity through solar panels, including photovoltaic power generation and solar thermal power generation. Wind energy, using wind turbines to convert wind into electricity. Wind energy is a common renewable energy source. Hydropower, utilizing water flow or water level differences, including hydropower generation, tidal energy, and ocean energy. Geothermal energy, using the Earth's internal heat and converting it into electricity through geothermal power stations. Biomass energy, using biomass such as wood, agricultural residues, etc. to generate electricity or produce biofuels. Hydrogen energy, obtaining hydrogen through hydrolysis or hydrocarbon processes for energy storage or as an energy carrier. Disadvantages and environmental ecological hazards of solar energy. Solar energy is a clean and renewable energy source, but it still has some disadvantages and factors that may impact the environment and ecology. Disadvantages: unstable weather impact. Solar power generation relies on sunlight intensity, therefore, during cloudy days, nighttime, or winter with reduced sunlight, power generation efficiency decreases, requiring storage systems or auxiliary energy sources. Relatively low energy density. Solar panels have low energy density, requiring large-scale installations to generate sufficient electricity, which may increase land use demand. Manufacturing and handling costs. The production of solar panels involves high costs and energy consumption, and the chemicals used during manufacturing must be properly handled. Limited resources. The manufacturing of solar panels requires rare metals, and these resources are limited, potentially causing resource pressure. Environmental ecological hazards. Waste management. After the end of their service life, the recycling and disposal of solar panels may impact the environment. Harmful substances contained within, such as cadmium, lead, must be properly treated to avoid soil and water pollution. Land use pressure. Large-scale solar power plants occupy significant land areas, possibly impacting local ecosystems and natural landscapes. Use of chemicals. Certain chemicals such as corrosives, cleaning agents used during solar panel manufacturing and cleaning processes may cause environmental pollution. Termination of solar energy use and environmental ecological hazards. When solar panels reach the end of their service life, they may cause the following: environmental and ecological problems, toxic substances. Solar panels contain toxic substances such as cadmium, lead, and antimony. If not properly handled, they may pollute soil and water sources, threatening ecology and health. Difficult to decompose materials. The silicon and semiconductor materials inside the panels require a long time to decompose, easily accumulating into waste. Resource waste. Without an established recycling system, rare metals and other resources may be wasted, increasing resource pressure. Recycling difficulties. Material recycling requires technical facilities, but some regions lack corresponding infrastructure. Wind energy. Disadvantages: termination of use, environmental ecological hazards. Disadvantages of wind energy: instability, changes in wind speed and direction cause fluctuations in energy output. Space requirement: wind farms require large areas of land or sea, possibly affecting ecosystems and landscapes. Visual and noise impact: the appearance and noise of generators may affect the lives of residents. Impact on birds and bats: generators increase collision risks, threatening flying creatures. Termination of wind energy use, aging and decommissioning of generators. After reaching the end of their service life, the recycling and disposal of old equipment may cause impacts. Waste management: recycling and disposal of components such as generator blades face technical challenges and are prone to becoming waste. Environmental ecological hazards, ecosystem impact: land or sea areas used for wind farms may damage local ecosystems. Aquatic ecosystem impact: offshore wind farms disturb water bodies and may harm aquatic organisms. Marine construction impact: construction activities may affect seabed ecosystems and benthic organisms. Animal migration impact: wind farms may alter the migration routes of birds and animals. Hydropower energy, hydroelectric power generation. Disadvantages: termination of use, and environmental ecological hazards. Disadvantages of hydropower energy: ecological impact: the construction of large dams and hydroelectric power stations may destroy local ecosystems, including the biodiversity of rivers, lakes, and wetlands. Migration and ecological changes: dams obstruct the migration of fish and other aquatic organisms, altering aquatic ecosystems and causing ecological imbalance. Land submergence and population relocation: dam construction requires large areas of land, which may cause land submergence and community relocation, leading to social and economic problems. Geological risks: dam construction may increase geological risks, including earthquakes, landslides, and soil erosion. Termination of hydropower energy use, aging and maintenance of dams, the structures of dams and hydroelectric power stations age over time, requiring regular maintenance and updates. After the end of their service life, dismantling or modifying these structures may be technically difficult and cause environmental impacts. Reservoir and waste management: water reservoirs in hydroelectric stations may accumulate sediments and pollutants that require proper management. Dam dismantling may also generate large amounts of waste. Environmental ecological hazards: water pollution: dams may cause pressure and pollution on water bodies, affecting water quality and harming aquatic ecosystems. Greenhouse gas emissions, decomposition of accumulated organic matter may release methane and other greenhouse gases, impacting climate change. Changes in river channels and water flow, dams alter river flow patterns, affecting hydrological environments and ecosystems downstream. Land use pressure, dams and hydroelectric power stations require large areas of land, damaging terrestrial ecosystems. Geothermal energy, disadvantages, termination of use, and environmental and ecological impacts. Disadvantages of geothermal energy, geographical restrictions. The utilization of geothermal energy is limited by the distribution of geothermal resources, which can only be fully exploited in geothermal active areas. High initial investment. The initial costs of constructing a geothermal power plant are high, including drilling and equipment installation, which may hinder its widespread adoption. Resource depletion. Long-term extraction of geothermal energy may lead to the depletion of underground thermal water, reducing power generation efficiency. Proper management is necessary to avoid resource exhaustion. Geological risks. Geothermal areas may face geological risks such as volcanic activity and earthquakes, which could affect the operational safety of power plants. Termination of geothermal energy use, depletion of geothermal resources. Long-term or improper management may lead to the exhaustion of geothermal resources, forcing the termination of use. Sustainable development strategies are required. Technological upgrades. With technological advancements, older geothermal power plants may need to be upgraded or decommissioned, increasing the need for structural renewal. Environmental and ecological impacts. Ecological impacts on geothermal areas. The development of geothermal energy may impact local ecosystems, particularly during the construction of geothermal wells and power plants, potentially harming local flora, fauna, and water sources. Discharge of geothermal water. Geothermal water released during power generation may contain minerals and chemical substances, which could affect nearby water bodies and soil, particularly aquatic life. Gas emissions. Geothermal areas may contain underground gases such as hydrogen sulfide, which could be released during energy extraction and power generation, causing environmental pollution. Geological changes. Long-term extraction of geothermal energy may lead to underground geological changes, potentially causing irreversible and long-term impacts on local geology and ecosystems. Hydrogen energy. Disadvantages. Low energy density. Hydrogen has relatively low energy density, requiring large amounts of hydrogen to provide sufficient energy. This can lead to challenges in storage and transportation. High production costs. Most hydrogen production currently relies on steam methane reforming SMR or water electrolysis, which are relatively expensive methods and may depend on non-renewable energy sources. Energy conversion losses. Hydrogen production, storage, and conversion involve multiple energy conversion steps, each of which can result in energy losses, thereby reducing overall system efficiency. Storage and transportation challenges. Hydrogen exists as a gas at normal temperatures, requiring large volumes for storage and transportation. This presents technical and safety challenges, including risks of hydrogen leakage and explosions. Resource dependence. Current primary methods of hydrogen production depend on natural gas or other non-renewable resources, potentially leading to resource dependence and environmental concerns. Termination of hydrogen energy use. Immature technology. some hydrogen energy technologies are still in the development stage. If more competitive energy alternatives emerge in the future, it could lead to the discontinuation of hydrogen. Energy use. Economic and feasibility. If the costs of hydrogen production and utilization cannot compete with other energy forms, it may limit its widespread application. Environmental and ecological hazards, carbon dioxide emissions. Current major hydrogen production methods e.g. SMR may involve carbon dioxide emissions, conflicting with hydrogen's goal as a clean energy source. Promoting the use of renewable energy for hydrogen production is key to reducing its carbon footprint. Pollution during hydrogen production. The hydrogen production process may involve pollutant emissions, causing adverse environmental impacts. Safety risks in hydrogen storage and transportation. Hydrogen is a flammable gas, posing safety risks such as explosions during storage and transportation. Solid-state energy storage vault industry. Solid-state energy magnetic power generation combined with mineral storage vault. This is a potential green energy solution that integrates magnetic power generation technology with graphene energy storage technology. Below are the features and considerations of this energy system. Core technical features. Magnetic power generation technology. Due to the involvement of magnetic energy, a special phenomenon occurs: output-input. Adopting advanced magnetic power generation technology. Energy is efficiently generated through magnetic field control, effectively reducing energy waste. According to the principle of conservation of energy, input energy plus magnetic energy equals output electrical energy. Since there is zero friction during rotation, energy loss is greatly reduced. Through the intervention of magnetic energy, the output electrical energy far exceeds the input energy. Even though a small amount of energy is consumed by air friction, the effect is better in a vacuum environment. Unlike traditional generators, magnetic generators mainly utilize inertia for power generation. The electrical energy is first stored in a large graphene storage cabinet, and then the load is supplied by the storage cabinet, similar to the operation of a solar power system. The core condition of inertia generation is high-speed rotation with zero friction, where the rotating object is completely magnetically levitated, achieving a mass without weight state, similar to the operational principle of Earth's rotation. The magnetic generator's efficiency can last up to 20 years. When the magnetic performance of the powerful magnets declines, it can be restored through remagnetization, enabling reuse without causing resource waste or environmental pollution, making it truly a safe and environmentally friendly green energy. Solid-state energy graphene mineral storage vault. The excellent properties of graphene gray crystalline heterostructure make it an ideal material for energy storage, significantly improving energy storage density and efficiency. As a new type of energy-saving and environmentally friendly material, graphene performs excellently in photocatalytic reduction of carbon dioxide. Modified graphene oxide has an energy band range that covers the reduction potentials for reactions involving methanol and hydrogen, making it suitable as a catalyst for the photocatalytic reduction of carbon dioxide. Graphene powder is processed into modules through special techniques: secret recipe, blending, stirring, high-temperature extrusion molding, making it suitable for efficient energy storage. Special materials and applications. A special type of existing rock resembling maltstone gray crystalline heterostructure is used, possessing excellent inductive heating and storage performance. This material is a key raw material for global high-efficiency energy transmission and basic applications. Graphite, the main source for manufacturing graphene storage vaults, is processed through core technology grinding and physical preparation methods to produce 8th-layer graphene powder with high performance, enabling low-cost operation and efficient energy storage. Considerations: core technology maturity, the development and experimental phases of magnetic power generation and graphene-based solid-state energy storage systems have been completed. The next step requires advancing to the first stage of industrialization, initiating the dormant maltite gray crystal heterogeneous element, and ensuring performance capabilities for high temperature and low temperature resistance. Additionally, it is necessary to manage raw material processing, involving auxiliary liquid mixing. Cost challenges: the manufacturing costs of magnetic power generation equipment and graphene are relatively high, potentially impacting their commercial viability. Only within an intelligent manufacturing environment utilizing automated production processes can production costs be effectively reduced, thereby enhancing market acceptance. Sustainability: the solid-state energy system's sustainable industrial applications can extend to public, community services, vehicle manufacturing, defense industry, and AI robotics sectors. This system employs zero-carbon energy, operating in environments free of pollution and noise. Safety: compliance with relevant safety standards is required to ensure the stability of the energy storage system and to mitigate potential risks associated with high energy density storage systems. Main products of solid-state energy: magnetic power generation equipped with solid-state energy storage vault. Preconditions: before producing magnetic power generation equipment and solid-state energy storage vaults, it is necessary to first complete the high-end cable industry to obtain the activation components required for the solid-state energy module, used for integrating the main structures and accessories of buildings. At the same time, it is necessary to handle the complex production processes generated by the magnetic power generation equipment, the solid storage graphite main industry, and the high-end cable industry, transforming them into industry resources with extremely high added value. Core advantages: safety: the solid-state energy storage vault system equipped with magnetic power generation has high temperature resistance, extreme cold resistance, and explosion-proof performance. Even if an electric vehicle collides, it will not trigger a fire or burning risk. Environmental benefits: thoroughly solves the pollution problems caused by current electric vehicle batteries, avoiding long-term environmental hazards from scrapped batteries. Product applications: Application 1, self-supplying power system for electric vehicles, from factory to scrap without the need for charging, achieving true self-supplying power. Electric vehicles generate power while moving permanently disconnected from grid services, never needing to charge for life using solid-state energy storage and free energy power systems. Solid-state energy storage technology has great potential in solving power supply problems for artificial intelligence AI and electric vehicles EV. The following are specific explanations of how these technologies provide assistance. Magnetic power generation and solid-state energy storage equipment use magnetic fields to generate electricity, achieving high efficiency and environmental friendliness. These devices can help solve power issues in the following areas for AI and EV: stable power supply, magnetic power generation and solid-state energy storage equipment can provide stable and continuous power supply, which is especially important for AI computing centers and EV charging stations that require large amounts of electricity. Stable power supply can reduce interruptions in AI operations. Application 2, Solid-State Energy Storage Vault Power Supply Station, magnetic power generation, equipped with solid energy storage, forms a power supply system without connecting to the grid, at no cost and with no pollution. Establish EV charging stations at highway rest areas in mountains, wildernesses, or deserts, providing large amounts of free electricity, creating high profit, super strong business opportunities. Application 3, Multi-scenario applications, community and commercial, suitable for free power supply to community buildings, shopping malls, schools, and other locations. Special environments, supports independent power needs for offshore islands, hospitals, forest recreation areas, deserts, remote wilderness areas, or independent highway charging stations. Industrial and agricultural, provides stable power supply for AI, artificial intelligence, industrial electricity, agricultural electricity, and community streetlight projects, promoting industrial upgrading. National defense and military industry, yachts, drones, unmanned boats, electric airplanes, and national defense industries. Advantages, core features, environmental and process. Analysis of solid-state energy storage vault, title, Energy Technology Revolution Opening the Green Future. Dear guests, investors, and participants, welcome to this solid-state energy advantages, core features, environment, process, and analysis briefing session. Today, we will explore the innovative breakthroughs and investment opportunities of magnetic power generation and solid-state energy storage vault technology. This is a grand event about the future of energy. Let us join hands to embark on the journey of exploring green energy, and jointly promote the progress of global sustainable development. Part 1, Background and Importance of Solid-State Energy. Background, with the increasingly severe global extreme climate change, energy security, and environmental sustainability issues, the development of solid-state energy has become one of the key solutions to these challenges. Zero-carbon energy refers to energy forms that do not emit greenhouse gases during production and usage, aiming to mitigate climate change, reduce dependence on limited natural resources, and promote sustainable economic growth. Importance, climate change mitigation, solid-state energy is key to achieving a low-carbon economy, significantly reducing greenhouse gas emissions and protecting the Earth's environment. Energy security, reducing dependence on traditional energy sources such as oil and natural gas. Helps to enhance energy autonomy and lower sensitivity to geopolitical and price fluctuations. Environmental sustainability, solid-state energy reduces the overconsumption of natural resources, achieving balanced development between the environment and the economy. Economic opportunities, the development of solid-state energy can create vast economic development space, spawning emerging industries and injecting growth momentum into the economy. International cooperation, coordinated global development of zero-carbon energy promotes technological sharing and experience exchange, addressing the common challenges of energy and the environment. In conclusion, the development of solid-state energy is both a technological and cooperative challenge, and a shared goal to achieve a clean and sustainable future. Part 2, In-depth analysis of magnetic power generation technology. Magnetic power generation technology is an innovative technology that generates electric Current based on changes in magnetic fields. Below is an analysis of its core features and working principles. Working principle: core technology of magnetic levitation, power generation. Magnetic power generation technology is based on a bearing-less, zero friction, and shock-resistant design, utilizing the principle of relative motion between magnetic fields and conductors, zero friction, high efficiency rotation. In traditional generators, copper wires cutting through magnetic field lines produce induced currents, accompanied by impedance effects. Magnetic power generation adopts a disc-shaped magnet high-speed rotation design. Due to bearing-less zero-friction rotation, it can produce high rotational torque and overcome the impedance issues caused by the relative motion between magnets and copper wires. The high-speed rotating magnetic disc also has a flywheel effect, further enhancing efficiency and minimizing energy loss. Magnetic power generation design: in the entire generation device, the rotating body achieves complete suspension through magnetic levitation, only subject to air friction without any other mechanical friction. The zero mechanical friction system design ensures that energy consumption only targets non-conservative forces such as air friction, while magnetic and electric forces, as conservative forces, do not cause additional energy loss. Differences from traditional generators: mechanical friction from traditional rotating bearings causes energy loss, but our bearing-less design avoids this issue, achieving truly zero friction power generation. The uniqueness of this technology lies in overcoming the common energy loss issues in traditional power generation equipment through the principles of zero friction and magnetic levitation, significantly improving overall system efficiency. Advantages: zero carbon emissions, completely fuel-free, achieving true green energy production. Economic benefits: the initial investment cost of the system can be rapidly recovered through long-term stable operation. Multi-scenario applications, suitable for electric vehicles, community power supply, high mountain and wilderness electricity supply, and more, promoting industrial upgrades in multiple fields. Summary: magnetic power generation technology relies on advanced zero-friction design and magnetic levitation principles, breaking through the limitations of traditional power generation models and providing innovative solutions for clean and efficient energy utilization. Part 3: The Miracle of the Solid-State Energy Storage Vault, Characteristics of Solid Storage, a deep exploration of the outstanding properties of graphene and why it is an ideal material for energy storage. Storage efficiency enhancement, demonstrating how graphene storage vaults improve energy storage performance to achieve longer-lasting energy retention. Graphene is a two-dimensional material composed of a single layer of carbon atoms. It possesses excellent electrical conductivity, thermal conductivity, and mechanical strength, making it an ideal material for energy storage. The following are the miracle characteristics of graphene storage vaults. Miracle characteristics of solid storage: ultra-high surface area. The hexagonal single-layer carbon atom structure of the raw material graphene gives it a very large surface area, providing more space for energy storage and making it an excellent energy storage medium. Outstanding conductivity: the raw material graphene has extremely high electrical conductivity, allowing electrons to move freely on its surface, effectively improving charge transport efficiency and thus enhancing energy storage performance. Efficient energy storage: solid storage vaults can effectively store multiple forms of energy, including electrical, thermal, and chemical energy, and are widely used in storage technology, supercapacitors, and thermal Energy storage systems. Lightweight and high strength. The raw material graphene is lightweight yet has remarkable mechanical strength, which offers significant advantages in designing lightweight energy storage devices, helping to improve the overall performance of energy systems. Sustainability and environmental friendliness. The raw material graphene is composed of carbon atoms and, compared to traditional energy storage materials, does not contain harmful substances. Energy systems using solid-state storage vaults are more environmentally friendly and sustainable. Multi-field applications of solid storage vaults. Graphene storage vaults show great potential in multiple fields such as storage technology, supercapacitors, energy storage systems, and solar panels, becoming an innovative technology in the energy sector. The excellent performance of solid storage vaults brings revolutionary technology to energy storage, and their application will significantly enhance the efficiency of energy systems and promote the development of sustainable energy. Industry status and market analysis. Market prospects and investment opportunities. Green energy market trends. Analyze the growth trends and future outlook of the green energy market. Investment return forecast. Provide a clear investment return forecast, showing the potential benefits for investors' participation. The analysis of market prospects and investment opportunities is key to the success of emerging technologies. Green energy market trends. Growth trend. The green energy market is currently in a phase of rapid growth, driven by global concerns about climate change and sustainable development. Government support. Many countries are actively formulating and implementing policies to promote the application of green energy, providing important momentum for market development. Market position of the solid-state energy industry. Emerging field. Solid-state energy, as an emerging technological field, has attracted wide attention and investment, becoming a core component of the green energy market. Demand for innovative technology. The integration of magnetic power generation and solid-state energy storage vaults into a zero-carbon energy solution lights up the future of green energy, leading generational innovation. It holds the potential to become a future market leader. Investment return forecast. High potential return, with the rapid growth of the green energy market and the demand for green technologies. Solid-state energy projects are expected to bring high potential returns. Long-term stability. Green energy is closely related to global climate and sustainable development goals, offering investors a stable long-term investment return. Technical excellence and market potential. Innovative technology. Solid-state energy projects that integrate magnetic power generation and graphene storage technologies demonstrate highly efficient and excellent technological advantages, helping to provide energy solutions. Market frontier. Such projects are at the forefront of the green energy market, gaining favorable positions in the market. Sustainability trends. Social responsibility. Investors are increasingly valuing corporate social responsibility, and participation in solid-state energy projects helps shape the image of sustainable corporate development. Sustainable investment. Investors who focus on sustainable development over the long term are more inclined to support solid-state energy projects to achieve their investment goals. In summary, the fields of zero-carbon energy, magnetic power generation, and graphene storage technology demonstrate huge market potential and investment opportunities. This is a sector poised for development, especially in terms of innovative technology and market potential. Solid-state energy, sustainable development, and social impact. Commitment to sustainable development elaborates on the commitment of solid-state energy to long-term sustainable development, and how to achieve this goal through breakthroughs in technological innovation. Social impact explores the positive impact of solid-state energy projects on both local and global communities. They play an important role in the process of achieving sustainable development goals and bring positive effects on cultural and social aspects. Climate change, social impact, emerging technologies promote low-carbon manufacturing, help reduce emissions, improve air quality, lower greenhouse gas emissions, and reduce the risk of natural disasters. Sustainable development, reducing dependence on fossil fuels, promoting the use of renewable energy, achieving stable energy supply, and advancing sustainable development. Resource conservation and renewable energy, social impact, promotes the use of renewable energy, alleviates pressure on limited natural resources, and drives technological innovation and industrial upgrading. Sustainable development utilizes advanced graphene technology to improve energy consumption efficiency, reduce energy waste, and realize sustainable resource utilization. Emerging technologies driving economic growth, social impact. The application of new technologies creates job opportunities, promotes economic growth, and enhances the technological literacy of society. Sustainable development, innovative technologies become the core engine of economic transformation and sustainable development, driving progress in clean technology and environmental industries. Promoting global cooperation, social impact, solving global electric energy issues requires transnational cooperation. These technology applications promote international collaboration in addressing environmental and energy challenges. Sustainable development, leading the future of energy innovation. Join us to shape the future of magnetic power generation and solid-state storage. Integrating global cooperation helps share technology, resources, and knowledge, accelerating the achievement of sustainable development goals. Social participation and education, social impact. The introduction of emerging technologies has increased society's attention to the sustainability of solid-state energy, inspiring public participation in environmental protection and clean energy movements. Sustainable development, through education and publicity, deepens society's understanding of the value of sustainable development and promote the formation of sustainable lifestyles. In summary, the application of solid-state energy, magnetic power generation, and solid-state storage technology not only supports sustainable development but also creates a series of social impacts, promotes social transformation, economic growth, and increased awareness of environmental issues. Conclusion: driving the future of energy. Join the solid-state energy sector. The research, development, and application of solid-state energy storage technology is driving an energy technology revolution, achieving more efficient and sustainable energy utilization. This is not only a challenge of technological innovation, but also a critical opportunity to change the future energy structure and to open a new era in the energy sector. Leading the future of energy innovation, using solid-state energy to lead a new era of clean energy, opening a new chapter in clean energy for the future. Driving force of innovative technology, let magnetic energy lead the future green energy innovation, creating tomorrow together. Foundation of sustainable development, join the field of magnetic power generation and solid-state storage to build a sustainable future. Green jobs and economic transformation shape the future of magnetic power generation and solid-state storage, moving toward the light of a sustainable green future. Global collaboration, shared wisdom, illuminate the green energy of the future. Today's investment drives tomorrow's energy revolution. Environmental education and social participation. Environmental education is progressing steadily, gathering more strength to co-create a green future. Raising awareness, changing lives. Solid-state energy storage vaults light up the future. Green energy leading the path of generational change. Green cities and sustainable buildings. The green transformation of cities and buildings is a key step toward a green future. Moving toward a green future is a shared adventure. Only through global cooperation and collective effort can we face this moment full of challenges and opportunities. Financial support needs analysis. Solid-state energy storage vault industry, factory construction planning, Phase 1, high-end cable industry automated production equipment. In the initial phase of the solid-state energy storage vault development, automated production equipment for high-end cables has been gradually introduced. One automated machine can replace the workload of 30 workers, achieving fully unmanned production, significantly improving production efficiency, effectively addressing labor issues, and avoiding potential challenges from labor union activities. Production features, operating 23 hours a day with a 3-shift system to ensure efficient production and equipment rest. Each shift is overseen by a factory engineer to ensure production quality and stable yield rates. Production capacity is 3 to 5 components per minute. Equipment lifespan is about 15 to 20 years, with regular replacement of certain parts required to maintain stable operation. Capital requirements, targets, right arrow initial capital, $30 million. Right arrow midterm capital, $85 million. After establishing a high-performance power cable production base and achieving mass production, the company plans to launch an IPO on the U.S. stock market within 1 to 2 years to raise additional operating capital. Phase 2, Solid-State Energy Operational Prototype, establish an assembly and manufacturing plant in Taiwan to serve the Asia-Pacific region. The solid-state magnetic energy generator has been manually built and has successfully passed operational testing, demonstrating stable and highly efficient performance. This marks a major technological breakthrough in the development of solid-state energy and lays a strong foundation for future large-scale applications. Capital requirements, targets, right arrow initial capital, $300 million. Right arrow midterm capital, $500 million. Key focus areas, right arrow manufacture solid-state storage units and complete product assembly. Right arrow integrate magnetic energy generation technology with solid-state storage products to expand market share. Right arrow cooperate with electric vehicle manufacturers in the Asia-Pacific region to build critical energy supply chains. Timeline, right arrow Taiwan plant, expected to begin production between Q3 and Q4 of 2029. Right arrow planned plant locations, coastal areas between Dayuan District, Daowen City, and Hsinchu. Daliao and Linyuan districts in Kaohsiung City. Areas surrounding Jiasu Township, Pingtung County. Phase 2 continued, establish a manufacturing plant in Texas to serve the Americas market. Capital requirements, targets, right arrow initial capital, $700 million. Right arrow midterm capital, $1.2 billion. Key focus areas: manufacture solid-state storage units and complete product assembly. Integrate magnetic energy generation technology with solid-state storage products to enhance market share. Support the electric vehicle industry in North America and the energy integration needs of residential communities in South America. Timeline: Texas plant, expected to commence operations and supply the market between Q2 and Q4 of 2029 to 2030. Phase 3, launch the world's first truly self-charging electric RV project. Objective: establish a manufacturing and assembly plant in Texas focused on assembling electric RVs and container truck heads, equipped with on-the-move power supply systems, eliminating the need for external power connections. Capital requirements, estimated at $3.50 to $4 billion. Timeline: Texas plant, expected to begin mass production between Q2 and Q4 of 2033 to 2035. Factory design concept: plant size between 80,000 and 150,000 square feet, with high ceiling designs. Layout, including production lines, warehouses, and independent entrances and exits. Case study on international financial policies, analysis of solid-state energy industry and international financial policy trends. The solid-state energy industry, as a key area of the next-generation energy revolution, is becoming a focus of attention for global capital markets and policy makers. As the global carbon neutrality goals advance, governments of various countries are actively deploying solid-state energy technologies through financial policies and capital guidance, forming a clear trend of industrial acceleration. First, in terms of capital flow, international financial institutions and sovereign wealth funds are concentrating resources into technology platforms that possess long-term energy storage capabilities and high safety. According to a report by the International Energy Agency (IEA), global direct investment related to solid-state batteries and energy storage has increased from approximately $5 billion in 2020 to over $18 billion in 2024, with a compound annual growth rate exceeding 30%. The valuation of solid-state energy enterprises in the capital market continues to rise, indicating strong market expectations for future technological leadership. Second, on the policy side, major economies have incorporated solid-state energy technologies into national-level strategies. The European Union's Innovation Fund has listed solid-state energy projects as key investment targets. The U.S. Department of Energy (DOE) has launched the Long-Duration Storage SHOT program, setting a target of reducing storage costs by 90% by 2030, clearly supporting the R&D and commercialization of solid-state energy technologies. In addition, Japan, South Korea, and China have also launched special financing programs and technical subsidies to promote domestic companies' participation in international competition. Third, in the application of international trade and financial instruments, export credit agencies such as the US Exim Bank and Korea Exim Bank are using insurance, guarantees, and concessional loans to assist their domestic solid-state energy technologies in entering emerging markets. This strategy of combining financial policy with industrial policy is reshaping the global energy supply chain and fostering a new wave of technology and capital integration. Overall, the solid-state energy industry has entered a growth cycle driven by policy stimulation, capital acceleration, market expansion. In the next 5 to 10 years, solid-state Storage is expected to achieve large-scale application in fields such as electric vehicles, distributed generation, and smart grids, and will also become an important component of national financial policy, competition and energy security strategies. Industry participants should closely monitor trends in international financial policies, flexibly utilize global capital and policy incentives, and seize growth opportunities. Local development of the solid-state energy industry, dedicated financial support framework for the energy storage industry, development of magnetic power generation equipped with solid-state energy storage, and industry chain expansion. The solid-state energy industry is striving for the development of sustainable industries with full commitment. Capital raised from the IPO market will be insufficient. Return on investment, according to financial forecasts of the solid-state energy industry, within the first 3 years. After the completion of the factory, the annual operating revenue will reach $300 million, with an annual profit margin of over 28.9%. Investors can achieve returns within 3 years, and as market share gradually expands, the revenue and profits of the solid-state energy industry will maintain stable growth, providing long-term tangible returns to investors. Phase 1, Market Sales and Profitability Assessment of the High-End Power Cable Industry. A detailed assessment will be conducted on the U.S. domestic transmission cable and distribution panel markets, evaluating market size, demand, and long-term potential. This phase lays the foundation for the development of solid-state energy and provides critical early financial support. U.S. Home Appliance Market Analysis. According to market forecasts, the U.S. home appliance market is expected to reach approximately $29.1 billion by 2025, with a compound annual growth rate CAGR exceeding 2.5% over the next few years. Distribution panel market outlook. An in-depth analysis of the U.S. distribution panel industry will focus on sales volume forecasts and profit margin estimates to identify strategic investment opportunities. Portable power station market. According to Fortune Business Insights, the U.S. portable power station market was valued at $213.39 million in 2022, and the CAGR from 2023 to 2030 is projected at 8.32%. Public data also shows that the global market size in 2022 was $1.23 billion, expected to reach $1.78 billion by 2032, with a CAGR of 3.8%. North America dominated the global portable power station market, with a market share of 42% in 2022 DC power supply market. In 2024, the US DC power supply market size is expected to exceed $426.53 million, and it is projected to reach $755.89 million by 2037. From 2025 to 2037, the market is expected to grow at a CAGR exceeding 4.5%. Right arrow. Major driving factors include continuous growth in demand for LED products, increasing penetration of smartphones, accelerated implementation of Internet of Things IoT technologies, electric power transmission and distribution T&D market. In 2022, the US T&D market reached USD 82.96 billion, and the projected CAGR in the coming years is 2.95%. T&D is a key infrastructure component ensuring efficient and reliable delivery of electricity from power plants to end users. This sector also provides critical financial support for Phase 2 of the solid-state energy industry. Right arrow major driving factors include, continuous growth in demand for LED products, increasing penetration of smartphones, accelerated implementation of Internet of Things IoT technologies, electric power, transmission and distribution T&D market. In 2022, the US T&D market reached USD 82.96 billion, and the projected CAGR in the coming years is 2.95%. T&D is a key infrastructure component ensuring efficient and reliable delivery of electricity from power plants to end users. This sector also provides critical financial support for Phase 2 of the solid-state energy industry. Right arrow Phase 2, new generation of independent power technology combining magnetic power generation and solid-state storage. Our magnetic power generation system, combined with solid-state storage, can achieve completely independent power generation, no grid connection, zero risk, zero pollution, zero operational cost. The high-efficiency parallel generation system can support up to 5 magnetic generators operating in parallel, supplying energy to large solid-state energy storage cabinets. The device simulates the function of a miniature power plant. Right arrow, it can meet the following energy demands: electric vehicles and AI servers, residential buildings and shopping centers, schools, hospitals and public infrastructure, forest parks, off-grid islands, and remote areas. High-value industry chains often generate waste that is difficult to handle and requires high temperature incineration. To ensure environmental compliance, the solid-state energy industry transforms such waste into high-value-added products, maximizing profit margins while supporting sustainable development. Right arrow Phase 3, the world's first self-powered electric RV, pioneering a new era of renewable mobility. We plan to establish an automotive assembly plant in Texas, USA, focused on building the world's first completely self-powered electric RV and EV. These vehicles will generate electricity while driving, eliminating dependence on charging stations and setting a new standard for off-grid mobility. Right arrow market potential and strategic positioning, revolutionary product, charging-free EV. Solid-state energy industry's flagship solid energy product enables EVs to operate from factory to disposal without any external charging, becoming a game changer in the EV industry. This will be provided as a key technical solution to global EV manufacturers. Huge global demand. According to industry estimates, EV manufacturers in Japan, the US, and Europe have daily demand ranging between 5,000 and 8,000 units, indicating massive market potential, strong profitability, and considerable returns. Promoting standardization and reducing investment risk, risk and countermeasures, risk analysis. The solid-state energy industry may face risks such as market competition, technological changes, and policy risks. The industry will respond through continuous technological innovation, enhanced market research, and flexible adaptation to policy changes. Risk response measures. The solid-state energy industry will increase R&D investment to maintain technological leadership. It will establish a flexible market response mechanism to adjust strategies in a timely manner. It will also maintain close communication with policymakers to ensure compliant operations. Conclusion and call to action. The strategic significance of global marketing for solid-state energy storage cabinets. Global cooperation strategy, strategic alliances, establish deep cooperative partnerships with leading global electric vehicle manufacturers, AI server producers, and energy management companies to promote market integration, share resources, and jointly drive industry innovation and sustainable development. Regional cooperation, collaborate with local electric vehicle manufacturing partners in key markets across the Asia-Pacific, US, and Europe to deepen cooperation, enhance industry efficiency, and improve market responsiveness. Cross-border technical cooperation, work with internationally renowned research institutions and universities to promote the research and industrial application of forward-looking technologies. Brand globalization, enhance global brand influence and expand market share by participating in international exhibitions and media promotions. Distribution channels, establish a global regional authorized sales agency system, responsible for regional operations. Using a borrowed ship to go to sea model, led by local companies, industrial and commercial news promotion, rolling style media reports, internet marketing, and the management of distributor networks to sell products to electric vehicle manufacturers. Market forecast and financial benefit analysis. Market forecast, the global solid-state energy and self-charging free electric vehicle market is expected to expand at a compound annual growth rate CAGR of 25%. The Asia-Pacific, United States, and Europe will be the main growth-driving regions, with the penetration rate of new energy electric vehicles expected to reach 43%. Financial benefit analysis, by 2030, the company is projected to achieve $12 billion in revenue, with a gross profit margin remaining above 56%. Return on investment ROI is estimated to exceed 37%, with operating profit growing steadily year by year. Follow-up development direction and cooperation proposal for the solid-state electric energy industry. The following presents the market prospects and investment opportunities in the fields of solid-state electric energy, magnetic power generation, and solid-state storage systems. Market trends in the solid-state electric energy industry. Growth trend. The green energy market is currently experiencing rapid growth, driven by global attention to climate change and sustainable development. Government support. Many countries are actively formulating and implementing policies to promote the application of green energy, providing important momentum for market development. Market position of the solid-state electric energy industry. Emerging field. As an emerging technological sector, solid-state electric energy has attracted widespread attention and investment, becoming a core component of the green energy market. Demand for innovative technology. The integration of magnetic power generation and solid-state energy storage systems offers a zero-carbon energy solution that lights up the future of green energy and leads generational innovation, with the potential to become a future market leader. Investment return forecast for the solid-state electric energy industry. High potential returns, with the rapid growth of the green energy market and the demand for green technology, infinite possibilities lie ahead. Let us lead the future of energy innovation and shape the future of magnetic power generation and solid-state storage together. The solid-state electric energy projects are expected to bring high potential returns. Long-term stability. Green energy is closely related to global climate and sustainable development goals, driving the future of energy. Join us in the field of magnetic power and solid-state storage. It offers investors long-term, stable, and high-profit investment returns. Technical excellence and market potential of the solid-state electric energy industry. Innovative technology. the solid-state electric energy project, integrating magnetic power generation and graphene storage technology, demonstrates high efficiency and outstanding technological advantages, contributing to energy solutions. Market frontier, such projects are at the forefront of the green energy market and gain favorable positions in the market. Sustainability trend in the solid-state electric energy industry, social responsibility, investors are increasingly valuing corporate social responsibility. Participation in solid-state electric energy projects is conducive to shaping the image of sustainable corporate development. Sustainable investment, investors with long-term focus on sustainable development are more inclined to support solid-state electric energy projects to achieve their investment goals. In summary, the fields of solid-state electric energy, magnetic power generation, and graphene storage technology show great market potential and investment opportunities. This is an area with development prospects, especially in terms of innovative technology and market potential.